Well, finally got this thing finished and programmed and running. I'll turn this on real quick. Right now I've got it running through a Fibonacci sequence program. But I thought I'd go real quick through it and go over the departures that I took over from Ben's design. Here's the clock module. Got my switches up here for the bus so I can hand enter values in there. This is pretty much the same as Ben's, except that I didn't do the third 5 timer. I didn't think it really needed it, but I do occasionally get bounces from this. I'm not really sure why. If somebody can see my thing there and see if there's something obvious. See, the other thing, I've got a dedicated stack memory here. Got dedicated RAM for the stack. Here's the LED showing the value on the stack, and these counters, up-down counters, the 169s. You can see the stack's doing some stuff there. Let's see, what else do I have here? 16-bit RAM address with what's it, 64K of RAM in there. Here's my 16-bit program register or instruction register. This has got some different things going on here. I'll explain them in a sec. Here's my also a 4-bit micro instruction counter. And so this is kind of weird. So this one holds the instruction, and it's actually only 7 bits for instructions, or the instruction itself, it can be 7 bits long, and this holds the argument for the instruction. And the reason I did that is because this comes through and there's a selector in here. So if the inputs, or outputs, which are multiplexed with these guys here, so you've got a 4-bit input selection, 4-bit output selection. So I have between 1 and 15 or whatever output that it selects. If they're all 4, if they're all on, all 4 of the bits are on, then it uses this argument to decide where you're inputting and outputting. So for instance, if the input is all ones, then it takes the first 4 bits of this argument, and then it uses that as the decoder, or to send to the multiplexers to turn it on or off, whatever. Same for the outputs. So with 8 bits here, I can select input and output from the code, which seems pretty handy. I've got a 24-bit control word, these EEPROMs here. I've got 4-bit flag register, carry 0, a flag for when A and B are equal, and a flag for when A is greater than B. Let's see what else is different over here. Oh yeah, dedicated program memory. Well, here's my instruction, the current instruction that we're on, and the 16-bit program counter. And actually, I had to compromise a little bit. This is actually only a 12-bit program counter. I've got a little 8-bit register and a 4-bit register. I ran out of room on this breadboard, and I didn't really want to spill it over into another board. But so I have just using 12 bits for the program, so that's what, 4,000 bytes. Then I've got this selector here, so the first 3 switches on there select the other addresses, so I can store, a few, I think 8 programs that are 4,000 lines long, and I can switch between the programs using that. The registers are the same as Ben's design, except I switched out for the ALU. I've got these 74LS181s for the ALU. I did build the ALU based on Ben's design, but after I ran into the limitations of it, I decided, well, I'll use this instead. All of this is the same LCD screen. Again, I've got the multiplexers down here that use these bits to do the inputs. I have the inputs coming out here, outputs out of here. And then here again, here's my control word, 24 bits. Got lines for halt, reset. Next, which is different than Ben's design, he doesn't have that. Basically what it does is it shorts this circuit here, or not the circuit, but the cycle. See how it's not using that last bit? So the micro instructions can have up to 16 steps, 15 really, because the first is always the fetch cycle, but there's an instruction that will send us back to 0 so that you don't have to run through all 16 steps in order to get to the next instruction. Once that next symbol comes, it just goes on. And it is happening, but it's just kind of blipping through. You can't really see it. Program gets the next program on the thing. And so I have multi-byte instructions. So a lot of times I need to get the next program byte mid-instruction so that I can use it. 4 bits for input, 4 bits for output. And then the ALU takes 4 bits to select the function that you want. And then there's a mode bit that turns it from logic to arithmetic. An input to tell it when to save the flags. You can see it blipping there, and then the flags are occasionally changing. Usually they only change when it goes back to 0, or, well, I guess for 1, because they're never both 0, but sometimes they're both 1 on the Fibonacci sequence, and it'll flash by here in a second. There's the carry bit for when it wraps around back to 0, and then the control for the carry, and then the up-down direction for stack, and then the counter increase for stack. That's pretty much it. I'll post the code for this program so I can talk a little bit about what the actual instructions are. But there is a bug that I'm discovering the longer I run this. Every time it wraps around to 0, the stack decrements and it doesn't recover. So with the code, this should never really be. It should only flicker between 0 and 255, or I guess you could say 0 and -1, because every stack operation should move the stack pointer back to where it was. For some reason, it's getting stuck somewhere and not recovering from that. But anyway, here it is, all finished up. It's been 3 years, but it's done, ish.